Hi students, in this lecture I am going to discuss a rolling motion on inclined plane. Let us see. Consider an inclined plane which is fixed. So taking an inclined plane which is fixed. Suppose theta is angle of inclination. So now we are releasing a body on inclined plane. Release a body on inclined plane. So initial velocity equal to 0. Okay. Now we can see that once a body is released, it rolls. You can see rotation, it will be anti-clockwise. Once a body is released on inclined plane, you can see rotation is now anti-clockwise. Okay. So focus now, forces acting on the body. Okay. So one is mg downwards, normal reaction, normal to inclined plane, and next one frictional force. See carefully. Free body diagram. It is free body diagram. EMG, normal reaction, normal to incline, okay. It is CN. I am taking for weight mg two components along the incline, that is EMG sine theta, normal to incline, that is mg cos theta. mg cos theta. And if you observe, because of friction only, torque is produced. So when you are taking torque equation about center of mass, because of normal reaction and because of gravity, no torque is produced. And we can see here, rotation is anti-clockwise. That means frictional force at the contact must be up the incline. And remember, this is now static friction. So we have discussed in earlier lectures that whenever body rolls without slipping, friction will be static. Okay. And how to decide now direction of friction? So here you can see friction is upwards because torque is now anti-clockwise. Okay. Now focus force equation for center of mass. Motion is only along the inclined plane. So along the inclined plane net force. See what we can write. It is mg sine theta minus static friction. This is net force along the inclined plane. That is equal to m into ACM. Okay. And if you observe along the normal to incline, there is no motion for the body. That means normal to incline net force must be 0. That means normal reaction is equal to mg cos theta. Okay. Next. Now focus. Now focus a torque equation about center of mass. Okay. Torque equation about center of mass. It is Fs into Fs into R. That is equal to I into alpha. In the place of phi, I am writing it is mk square, where k is known as radius of gyration. Okay. I into alpha. That is equation. Now you can see relation between ACM and alpha. For contact point, there is no velocity. That means VCM should be equal to R omega. If you differentiate once, BCM equal to R omega, differentiate once, we get ACM equal to R into alpha because inclined plane is stationary. So for contact point, velocity must be zero. Okay, right. Now see what we can do. So take this one is second equation. Then Fs is equal to M A square by R square into ACM because I'm taking the place of alpha ACM by R. Okay, into AC. So here we want to calculate what is acceleration of center of mass and how much frictional force is acting on the body, right? So we have two unknowns, Fs and ACM, and we have two equations, right? Now see what we can do. Substitute this value in equation 1. Then see what we get here. In equation 1, substitute the value of static friction. mg sine theta is equal to mg sine theta is equal to m into ACM, m into ACM. It is now 1 plus, remaining is now 1 plus k square by r, k square by r square. So m gets cancelled here. So ACM equal to g sine theta upon 1 plus k square by r square. And we are taking that k square by r square as beta. K square by r square is beta. Okay. So that is now acceleration of center of mass. And once we are knowing that, we come to know what is static friction. We can substitute that in this one in the place of ACM. Okay. K square by r square, that is beta. So what we get here? See carefully, static friction is equal to m into, this is beta, that is beta. So beta upon 1 plus beta. Remaining is now mg sine theta. Okay. Cross check once. This is beta. So beta upon 1 plus beta. Remaining is now m g sine theta. This is now static friction. And we are knowing the value of beta, right? Suppose taking solid sphere, beta value 2 by 5. Hollow sphere 2 by 3. Disk 1 by 2. Ring, it is 1. Okay. That means for a given inclined plane, if you are taking same mass for all bodies, it depends on beta value. Okay. So we got acceleration for center of mass and we got static friction. Now, here one more thing is, if it is a smooth inclined plane, rolling without slipping is not possible because rotation is because of friction. So without friction, pure rolling on inclined plane is not possible because here condition we have taken inclined plane is fixed. Okay. Next, there must be sufficient friction to provide rolling without slipping. There must be sufficient friction. So now we want to calculate what should be the minimum coefficient of static friction so that rolling is possible without slipping. Okay. Then see what we can do. This static friction should be, less than or equal to limiting friction. Okay. This static friction should be less than or equal to limiting friction because we have learned that static friction is self-adjusting. Its range is from 0 to up to limiting value. Okay. Now substitute the value here. See what we get. Static friction beta upon 1 plus beta mg sine theta, that is now less than or equal to limiting value. It is mu s into normal reaction. Normal reaction how much? Mg cos theta. It is now mg cos theta. Okay. So now here, see the calculation part. mg gets cancelled. Remaining is now mu s. Mu s should be greater than or equal to equal to beta upon 1 plus beta into sine by cos, that is a tan, into tan theta. So minimum coefficient of static friction is beta upon 1 plus beta into tan theta. So friction value must be either this value or more than this value. Then only rolling possible without slipping. So whenever any question given basing on rolling on inclined plane, first we have to cross check is the given mu value is equal to this or greater than this. Then we come to know rolling without slipping is a possible or not. Okay. Next, see some simple questions basing on this. First, now some simple questions. Right. Suppose question is given like this: releasing releasing solid sphere, disk, hollow sphere, and ring. Okay. These four bodies are released on the top of the inclined plane, released from rest. Okay. Now question is that which body will reach bottom of incline in less time? Okay. Question is which body is reaching bottom of the incline in less time? Then see how to calculate. First of all, we know what is ACM. Okay. So ACM is known. ACM is known. Released from rest. So for all bodies, U value 0. U means UCM. Okay. Velocity of center of mass initially 0. Next, for all bodies, displacement is the same. So displacement I'm taking as a length of inclined plane. That is the same. We want to calculate time taken. Okay. Acceleration is known. U value is 0. L is same for all. We want to find out time. Then see which equation we have to use. Means using here equations from kinematics. Okay. So here we can write equation connecting these four quantities. That is S equal to ut plus half at square. U value 0. Half A value g sine theta upon 1 plus beta. Half A t square. Okay. Now you can see for all bodies displacement is same. Okay. So S is same for all. Next, g sine theta is same for all. Okay. Now what is remaining here? From this we can write t proportional to root of 1 plus beta. T proportional to root of 1 plus beta. If beta value is less, t will be less. That means that body reaches ground or reaches bottom of incline in less time. Okay. Now you can see for solid sphere, it is 2 by 5, right? 2 by 5 for solid sphere. For disk, 1 by 2. Hollow sphere, 2 by 3. Beta value. For ring, it is 1. Now see carefully. 2 by 5, 0.4. This is 0.5. So 0.4, 0.5, 0.67. This is 1. So this is least value is for solid sphere. That means it takes now least time to reach bottom of incline. So first it is solid sphere, next one disk, next hollow sphere, and last is ring. Okay. You can see in the place of disk, even we can take solid cylinder because for that also beta value 1 by 2. In the place of ring, even we can take hollow cylinder. Okay. Because for that also beta value 1. Okay. Like this, basing on kinematics, we can expect any question, right? For example, they ask question like, which is reaching bottom of incline, which is reaching bottom of incline with more speed. Okay. Then see where change comes. U0, U0, ACM is known. Displacement same for all. We want final speed, right? So equation connecting now u, v, displacement and acceleration. That means we can use now v square minus u square equal to 2 a value g sine theta upon 1 plus beta 2a s is l. Now we can see in this which are constants. L same for all. G sine theta, it is a constant. So from this we can write V proportional to 1 by root of 1 plus beta, right? If beta value is least value, V will be maximum. And we have seen that beta is least for solid sphere, right? That means it is having maximum speed, okay? Or we can get same conclusion by using energy conservation. Let us see how to get it by using conservation of mechanical energy. So using conservation of mechanical energy. Suppose this height equal to h. Okay. If a height is h, initially having only gravitational potential energy because we are releasing the body, no kinetic energy. When it reaches bottom of incline, this gravitational potential energy completely converts into kinetic energy. And while taking kinetic energy, we should be very careful. We have to take kinetic energy because of translation and because of rotation. Okay. Plus half 5 omegas. Now in this inclined plane is stationary. Therefore, we can write omega equal to Vc by R. That means we are going to get half m Vc square into 1 plus beta. Okay, that is equal to mgh. Now see carefully. From this, what we can conclude? For all, mgh is same. If you are taking all having same mass, mgh is same. Okay, remaining. Or I can do one thing. M gets cancelled. What else left from here? From here, velocity of center of mass is equal to 2gh upon 1 plus beta. Okay, under root. Bc equal to how much? Root of 2gh upon 1 plus beta. H is same for all, g constant. So Vc proportional to 1 by root of 1 plus beta. So either we can solve by using kinematics or by using conservation of mechanical energy. Okay. Next we have to focus one more important point. Here we have seen that when we are releasing the body, it is now rolling down the incline. Frictional force on the body is up the incline. Now question comes, if we project a body up the incline, means body is now rolling up the incline. When body rolls up the incline, what will be the direction of frictional force? Is it down the incline or up the incline? Let us see how to get it. Right. So we want to decide direction of frictional force when body rolls up the incline. Suppose a body is now rolling up the incline. Okay. Now we can see when body is rolling up the incline, omega value keep on decreases. I am repeating. When body is rolling up the incline, omega keep on decreases. Right? Omega keep on decreasing means torque must be torque must be opposite to direction of omega. In this diagram, omega is now clockwise. Omega clockwise. Omega clockwise means torque must be torque must be anti-clockwise. And we have learned that torque is only because of friction, because weight is passing through center of mass. Normal reaction is passing through center of mass. So because of these two forces, no torque is produced about center of mass. So about center of mass, torque is only due to frictional force. Okay. Therefore, so what we can do here, torque must be anti-clockwise because omega is a clockwise. Torque must be anti-clockwise. So torque anti-clockwise means friction must be up the incline. Then only friction provides anti-clockwise torque. So conclusion is that whether body is rolling up the incline or rolling down the incline, frictional force on the body will be up the incline. So this question is asked once in previous IIT. So conclusion is that whether body rolling up the incline or rolling down the incline, in both the cases, frictional force on the body is up the incline. Okay.